For the single effect evaporator system, we have vapor formed here. All the vapor which is formed is taken as the inlet for the compressor. The compressor is run mechanically so that it compresses the vapor from its inlet condition here, which is basically can be assumed as saturated vapor, to superheated vapor that is taken as the source of heat for our system. So the compressor increases both pressure and temperature for the vapor, and the hot vapor, which is taken from the outlet of the compressor, is entering into the tube bundle, inside the tube bundles in the evaporator, and it is the source of heat, where it is desuperheated first, and then it is condensed into liquid, which is basically the product, the distillate product that we're looking for. And the heat of condensation, which is liberated in the evaporator, is the source of heat that preheats the seawater from the feed temperature to the saturation temperature and evaporates part of it that makes the formed vapor and so on. The part that will not evaporate will be rejected at the saturation temperature. This way you have a couple of streams which are leaving the evaporator at relatively high temperature. The distillate, which is leaving at the saturation temperature, and the brine, which is leaving at the saturation temperature as well. The difference between them is just a few degrees in centigrade or Celsius. These hot streams that are leaving the evaporator are being used so that they can preheat the feed water which is coming. So have seawater that is distributed, part of it will enter to the brine heat exchanger. The rest will get into the distillate heat exchanger, where both streams are going to be heated to the feed temperature, and then they are recombined again before they are admitted to the evaporator to be sprayed in. So in this unit, we do not have a condenser because we do not need a condenser, but rather we have a couple of heat exchangers which are utilized so that we can make use of the energy associated with the rejected stream, rejected brine at high temperature, rejected distillate at relatively high temperature. Both of these energies are being made or made use of to preheat the feed. And accordingly, we can just, instead of throwing these streams at high temperature to the surroundings, we are using them for preheating the feed. So this is the basic idea that we have for this unit. What we wanted to look at then, after we talked about that these units are then throughout the world, they are not very much common as the units which are used by thermal vapor compressors, but they have a benefit, or they have a good feature, that they are a standalone units. You don't need to connect them to a boiler. All you need is a source of mechanical power to run the compressor, which can be an engine, a diesel engine, for example. It can be a wind turbine, or it can be a PV system, which is run by the solar energy to produce electricity, and the electricity can run the compressor. So that makes it some sort of a compact, stand-alone system that can be operated in remote areas without the need of having steam or a power plant to be connected to it. When we come to how the model equations would be, basically the basic equations that we have in the evaporator will not change much. We have a couple of heat exchangers where in these heat exchangers, we do not have condensation, but we have a hot stream of liquid that is being cooled down from TD, which is the distillate temperature, to T naught, which is the temperature of the distillate leaving the heat exchanger. The brine here, which is leaving at T brine, will be cooled to also a temperature that we call T naught. So the assumption that we are going to do is that the temperature of the distillate here, which is being cooled down, and the temperature which is brine of the brine, which is cooled down, they are both going to be cooled down to the same temperature. Is that necessary? No, it is just for the sake of simplicity of our calculations that we reduce the number of unknowns by assuming that this brine leaving the heat exchanger, the distillate leaving this heat exchanger, are leaving it at the same temperature T naught. On the other hand, we have T cooling water, which is coming in here, that is going to be heated up to T F, which is the feed temperature, we do not need an additional quantity of seawater. Remember, in the condenser, we said that we need the entry to be T cooling water plus T feed. The T cooling water will enter in, it will be preheated, and then we throw it away. And the reason was to make sure that all the vapor is condensed. Here we have no condensation. Accordingly, we just enter the value of m dot feed. This m dot feed will be distributed between these two heat exchangers so that it is heated up from T cooling water to T feed. And then the stream is taken to be entering to the evaporator where it will be sprayed. The evaporator will have a bundle of tubes, will have a mist eliminator, and then it is connected to a compressor, a vapor compressor that receives the vapor that leaves the evaporator. It compresses it, heats it, and then the heated vapor is going to enter into the tube bundle inside again. So when you are looking for the analysis, I would probably put the kind of assumptions that are made for running the unit. This is the temperature distribution that we have in both units. In the evaporator, we have steam, which is leaving the compressor at high temperature. It is superheated. When it enters the evaporator, it will desuperheat, which means that its temperature is going to drop sensibly from Ts to the saturation temperature at that given pressure. What pressure? It is the pressure leaving the compressor. So this is the TD that's going to undergo condensation at constant temperature, and then it will leave the unit at TD. So we have desuperheating, a part of sensible cooling, and then condensation. On the other hand, the feed is going to enter at a temperature TF, where it will be sensibly heated from TF to TB, which is the saturation temperature of the brine. And then it is going to undergo evaporation for some of it, and the rest is going to be rejected as T brine. The vapor that will form is going to form at a temperature less than the TB by the boiling point elevation. So the difference, again, as usual, between TV and TB is the boiling point elevation. We will see here that in this profile that we have part of the energy is sensible and part is latent. Part is sensible and part is latent. We are going to account for this while we are writing the energy balance. But when it comes to the area calculations, again, we are going to assume that the area needed for sensible heating in the low temperature side or on the high temperature side is too small, and we are going to simply assume that as if it is occurring at a constant temperature difference. This is an approximation to make it easy for us to calculate the surface areas. So this is as far as the temperature distribution in the evaporator is concerned. And then when it comes to the inside the heat exchangers, we have two heat exchangers where if we're going to look at each one of them separately, we can say that we have a brine heat exchanger where the brine temperature is going to reduce from T brine to T naught. And we have, on the other hand, seawater coming in the shell side where it will be heated from T cooling water to T feed. This happens in one heat exchanger. In the other heat exchanger, we have the distillate coming inside the tubes, for example, so that it will be cooled down from T distillate to T naught. And while it is being cooled down, it will be heating the seawater from T cooling water to TF. So the kind of approximation that we are making here is that this temperature, which is the distillate leaving the heat exchanger, is equal to this temperature for the brine leaving the heat exchanger, so that the analysis becomes a little bit simpler. We have seen last time when we discussed this issue, or when we discussed this system, that we had the system made in a way that For some of the units, these two are combined together in one heat exchanger, and then the profile will be looking like this. The distillate is cooling down from TD to T node. The brine is cooling down from TB to T node, and all the feed is being heated up from T cooling water to T feed. So it can be a single heat exchanger with 3 streams, or the usual analysis that we had earlier, which is that we have a couple of heat exchangers, and that matches the figure that I've shown a while ago, which is basically this kind of arrangement. So we have a couple of heat exchangers. One of them is for cooling down the condensate, while the other one is for cooling down the brine, where both of them are being used to heat the seawater up, or to preheat the seawater to be more accurate. When it comes to typical values that we have, Ts minus Td is between 4 to 10 degrees centigrade. And by the Ts and the Td, to remind you, they are these. This is basically Ts, which is temperature of the seawater, temperature of the vapor leaving the compressor. It will be desuperheated from Ts to Td in the evaporator. This temperature difference is going to be somewhere between 4 to 10 degrees centigrade, which is the degree of superheat. The difference between TB and TF is somewhere between 1 and 5 degrees centigrade, which is basically this temperature difference from TF to TB. This. Sorry, it should have been vertical. The temperature difference between TD and TB is again somewhere between 1 and 5 degrees centigrade, which is this temperature difference here. And the temperature difference again between T node and T cooling water, this is in the cold side heat exchanger, which is the temperature difference basically between these T node and the T water. Again, this is somewhere between 1 to 5 degrees centigrade. Why is that? Why these temperature difference are specified this way? Because we are going to make use of this temperature difference in calculating the heat transfer areas. And we need to make sure that the size of the heat exchangers will not be too big. If it is too big, then the initial cost is going to be too high. If the initial cost is too high, then the water cost will be high. So in order to have the operation in a way that is economic in terms of the cost of the produced water, these temperature differences are going to be kept. So these are some sort of a recommended range of temperature differences within the unit. The material balance, again, the first 4 equations are the same equations that we always see. Khalid, you had a question. Go ahead, please.
Yes, Doctor. Regarding the analysis here, when we reach to the mass of the distillant water, what temperature we consider? Is it the distillant or the TO?
The temperature of the seawater, which is leaving the evaporator, it is leaving at this temperature, TD.
TD. So we consider TD.
So it will enter as TS, it will cool down first to TD, and then it will keep as TD, and it will leave the unit as TD. The brine also is going to be, the feed will be heated from TF to TB, and it will remain as TB to leave the unit as TB. So if I'm talking about the temperatures of the streams that are leaving the evaporator, we have distillate, which is leaving here, and it is leaving at temperature TD. And we have brine, which is leaving at temperature TB. And both of these are at somehow elevated temperatures, 50s or 60s degrees centigrade. And these are the 2 streams that are going to enter the 2 heat exchangers for preheating the feed. Did I answer the question? Okay. So when it comes to the evaporator balance, then the feed which is entering into the evaporator is going to be, part of it will be, of all of it will be heated to TB, then part of it will be evaporated and the rest will be rejected as brine. And the salinity balance, definitely the distillate which is having here is having a value of 0 salinity. This is the usual assumption for thermal distillation systems, and accordingly, the m dot f xf, which is the salt balance, is m dot b xp. These two equations are additional equations. We normally write them, but when we come to solution, we don't have to consider these two expressions. They are just made as a rearrangement of these two equations to bring m dot b and m dot f in one side of the equation. But these two equations are not new. They are only manipulation of the first two equations. So equation number 1 and equation number 2 are the ones that we are interested in here. Then the feed which is coming, it will enter the two heat exchangers. So if I'm going to look at m dot feed, as it enters the two heat exchangers as one control volume, then the feed is going to be heated from T cooling water, and it will be leaving at a temperature of TF. So the two heat exchangers here are going to have Q heat exchangers is going to equal to the feed multiplied by the Cp into the temperature difference. We can break this down. For example, you can say that part of the feed, like alpha into m dot feed, is going to be heated from T cooling water to TF in one heat exchanger, say the distillate heat exchanger, and the rest, which is 1 minus alpha m dot feed Cp T feed minus T cooling water, will be heated in the brine heat exchangers. So if we are going to use two heat exchangers, then this is basically what we say here, that alpha is a fraction less than 1, which makes that the ratio of the seawater that will enter into the distillate heat exchanger, this is alpha, and this is going to be 1 minus alpha of m dot feed. So if alpha is 0.4, 0.4 of the feed is going to enter here, and the rest, which is the remainder, 0.6, is going to enter to the other heat exchanger. So this equation is written for the two heat exchangers together, and if you need to write it for each heat exchanger, then this is what you write. Then, so this is plus this. Then this one, or this part, is in balance with m dot distillate Cp T distillate minus T naught, while this one is in balance with m dot brine Cp T brine minus T naught, as we will see in the next slide. So this QH that we have seen previously for the two heat exchangers is written here as you can see it, m dot distillate Cp T distillate minus T naught. This part in particular is in balance with alpha m dot feed Cp T feed minus T cooling water, and this quantity, which is m dot brine Cp T brine minus T naught, is in balance with 1 minus alpha Cp T feed minus T cooling water. Then, if we consider these two equations together, we can do algebraic manipulation to reach for an expression for T naught. While you are solving a problem, do you have to consider this equation? The answer is no. This equation is not really needed. This is just some sort of algebraic manipulation to say that we have a closed form solution that will bring us the value of T naught leaving the two heat exchangers. But as a matter of fact, this equation and the previous equation that has been splitted to these two parts is what you need. The evaporator, what will happen inside the evaporator is the Q evaporation will be looked at from two sides. You can look at the heat exchange or the heat transfer in the evaporator from here. It is basically made up of two parts. Part which is this. So Q evaporator here can be m dot distillate or m dot vapor into Cp into T steam minus T distillate. So this is the kind of sensible heating that occurs here. Plus m dot distillate into HFG of steam. So this is the energy given by the heated vapor, the vapor that leaves the compressor at high temperature. This is the kind of energy which is transferred from this to the brine. This also temperature is going to be heating the feed from TF to TB, and it will evaporate part of the feed, m dot, distillate into HFG of the vapor. This part of the equation we have written before for the single effect evaporation and the single effect evaporation with thermal vapor compression. But it is this part here, which is not m dot s HFG as we used to write it before, but it is made of two components. The m dot steam into HFG is this, but there is a part of desuperheating that occurs in, and this part is the one that's given by this expression. So that these two equations are making the energy balance that we have in the evaporator, which is being taken care of by these two expressions here. One of them is for the cold side, for the feed side as it's being heated, and one of them of the steam side, which is the evaporated vapor that goes through desuperheating and then condensation. These three equations that you see here are not new to us. It is just, again, some sort of algebraic manipulations. Why I'm writing them here in that presentation? Because this is just addition manipulations that it does not add any value to the solution, but they are written in the book so that you would see why these equations are there. The equations are simply because they will give us the value for TF as separate value. It's a value at the left-hand side with all the other parameters on the right-hand side so that you can calculate TF easily. That's all. But otherwise, there's no added value of these three equations that we have here because they are not new. They are just algebraic manipulations of the equations that we have written before. Surface area, as you have seen, Q evaporator, what we do here is that we can neglect the part of sensible heat when it comes to the area calculations and assume that in the evaporator we have just a constant temperature difference. One of them is TD and the other one is TB. The part of sensible heating here and the part of sensible cooling here is going to be neglected. Otherwise, if we are going to consider this and consider this, then we'll have to worry about a log mean temperature difference for each one of them. So just to make our life easier for the evaporator, we just say that it is U, overall heat transfer coefficient, into the area, into delta T, which is in balance by the Q evaporator that we have written before. This expression and this expression are nothing but Q evaporator that we have written here. So actually, this Q evaporator that we've written is in balance with an overall heat transfer coefficient into the area into delta T, which is what you see here in this expression up here. And then finally, for the couple of heat exchangers that are used to preheat the feed, then basically we have one heat exchanger in which the distillate is being cooled down to T naught in order to preheat the feed from T cooling water to T feed. So we have basically delta T1, we have delta T2, so that the log mean temperature difference can be calculated, delta T1 minus delta T2 divided by ln delta T1 over delta T2, so that Q, say that now we're talking about this heat exchanger, which is the distillate cooling heat exchanger. So Q here is going to equal to, definitely it is the m dot distillate Cp into T distillate minus T naught. This is in balance with the overall heat transfer coefficient for the distillate heat exchanger area of the distillate heat exchanger into the log mean temperature difference of the distillate heat exchanger. On the other hand, for the other heat exchanger, where the brine is going to be cooled down from T brine to T naught, heating the feed or part of the feed from T cooling water to TF. Again, here we have delta T1, we have delta T2, and then we are going to calculate the log mean temperature difference for the brine preheater. Accordingly, this Q for the brine preheater, if this is QD, then this is going to be Q for the brine preheater, is going to be the area of the brine preheater, overall heat transfer coefficient, and the log mean temperature difference for the brine preheater. So when you look at it, there's nothing new here. It's just we are applying the information that we have known for each one of these heat exchangers, and there is a link between the two heat exchangers, and the link we have seen before in that slide here, that the seawater which is entering that preheater is being splitted to a fraction alpha and a fraction 1 minus alpha, so that we can heat the seawater from T cooling 1 to TF, cooling 1 to TF, by the brine stream and by the distillate stream which is leaving. And these are the expressions of the log mean temperature differences here. Then, if we are interested in how the whole performance of this unit is going to be, we don't have steam coming in, so we cannot calculate a PR for this unit. There's no PR, because PR used to be m dot distillate over m dot steam. We don't have steam. And the kind of energy input here is basically coming from a compressor. So what we are going to write here is, it is going to be given in terms of a specific energy or specific power consumption by the compressor. This equation has been taken from Thermo 1, Me2O3, for running a compressor, where gamma is the specific heat ratio. So gamma basically, which is basically Cp over Cv of the vapor that we are using. So gamma into the pressure in the intake, specific volume in the intake to the compressor, into compressor efficiency, into gamma minus 1, into the pressure ratio, P of steam over P over the intake vapor to the power gamma minus 1 over gamma minus 1. So this will give us the value of work here as kilojoule per kilogram. If you want to calculate the power, then you multiply this by how much kilogram per second of steam or of distillate that you have, then you can calculate basically the power in terms of kilowatts. So the kilowatts is small w multiplied by m dot distillate. That will give us the power needed by the compressor in terms of kilowatts. So here we are not going to talk about a performance ratio, but rather we are talking about specific power consumption. Talking about specific power consumption makes us, in a way, we are able to compare the performance of this unit with the performance of a system which is pressure driven, like the RO, reverse osmosis, or the FO, forward osmosis, because basically when we are looking out about specific power consumption, we are looking for how much kilowatt hour per cubic meter of distillate water. And we use this expression to compare the performance between units so that it becomes some sort of a measure of the performance of the desalination systems which are operating by a prime mover, or operating by either a pump or a compressor like the one that we can see here. And there are special vapor compressors, by the way. Not every compressor can compress vapor, but there are special brand or special type of vapor compressors that are taking the water vapor in and compressing the water vapor to higher pressure and temperature. Let's take a numeric example, unless you have any questions so far. If not, then we are going to take an example. This example is given in the book, which is there in the blackboard, fundamentals of saltwater desalination. It is considering a single effect mechanical vapor compression system, which is designed to take care of the following parameters here. We need a distillate of 1 kilogram per second. CP value of the vapor is 1.884. CP of the seawater is, or the other streams basically, is assumed to be 4.2. And this is another approximation because we know that the seawater would have a CP value of 3.8 almost, whereas the sweet water has a capacity of 4.2 kilojoule per kilogram Kelvin. But this is the input anyway. The overall heat transfer coefficient in the evaporator is given as 2.4 kilowatt per meter square centigrade. For the brine preheater, 1.5 kilowatt per meter square centigrade. And for the distillate preheater, or distillate heat exchanger, it is 1.8 kilowatt per meter square centigrade. Definitely, kilojoule per second is kilowatt, which is this. The intake seawater comes in at a temperature of 25 degrees centigrade. The distillate is at a temperature of 62 degrees centigrade, which is the condensed distillate. The degree of superheat in the compressor is 3, so Ts is equal to T distillate plus 3. The brine saturation temperature is 2 degrees less than the distillate, so it is 60 degrees centigrade. The feed is coming at 42,000 ppm, and the brine is rejected at 70,000 ppm. And finally, the compressor efficiency is 58.9%. What we need to do here is to do the analysis by calculating how much is the heat transfer areas, how much is the power consumption for the unit, so that we can estimate how good or how bad the performance is. So this is a typical example of single effect mechanical vapor compression, and we may do it together, like going step by step to see how we can solve this. And I would prefer that you follow the solution that you are going, because in the book he might be using the ready-made equations that he did after the manipulations, and I don't want us to memorize equations. We better go through like a simple heat analysis step by step. So I'm going to close this, and I'm going to open like a white screen where you can we can basically go sort of a step by step in the solution. So what we have here basically is a single effect mechanical vapor compression system, and we have information given to us, so that salinity of the feed is 42,000 ppm. Salinity of the rejected brine is 70,000 ppm. Then we know that the distillate quantity which is needed as given is 1 kilogram per second. Then, as usual, what we begin with here is the mass balance expression. So m dot feed is equal to m dot distillate plus m dot brine. This equation is common for all types of conventional desalination systems. We'll see that we have used this for the single effect evaporation, with thermal vapor compression, single effect evaporation with mechanical vapor compression, multiple effect evaporation, multiple stage flash, and even for the RO. This equation is always there because always we have a stream of seawater coming in. Part of it will be converted into sweet water and the rest will be rejected as brine. So this equation is always there in addition to this equation, which is X feed into m dot feed is equal to X brine into m dot brine. These two equations are two equations and three unknowns. We know one of them, which is m dot distillate. So they become two equations and two unknown, m dot feed and m dot b. We know the salinity of the feed and salinity of the brine. So what we can do is basically, maybe we can eliminate m dot brine by saying that m dot brine is m dot feed x feed over x brine, and we substitute it here, so the equation becomes a function of m dot feed alone. Then we solve it, and by solving it, we get the value of m dot feed. You have done that already in the third problem of the midterm exam, that m dot feed here is going to equal to 2.5 kilogram per second, and accordingly m dot brine is 1.5 kilogram per second. So that is our first thing to do, which is basically the mass balance. What is what should be there in the in the example? It was not given explicitly. It's talking about the values of HFG. Basically, what he relied on is that since it is an example, then we are able to get into the steam tables or get into the ES and obtain the values of HFG. So HFG of the distillate is 2.354 kilojoule per kilogram, whereas HFG at the brine temperature is basically 2.359 kilojoule per kilogram. Then, when we need to talk about the energy balance, we are going to start with, so here I'm going to say energy balance. Then Q in the evaporator is basically, in the evaporator, remember, we have the feed coming, the feed flow rate, and the feed flow rate is sensibly heated from TF to TB. And part of it is going to evaporate so that it becomes given by that expression here. So sensible heating of the feed from TF to TB, and part of it is going to evaporate, which is the 1 kilogram per second that we are getting as a product here. So this is our first expression here. And when we look at that expression, you can see also the feed is going to be, or the QE basically, is going to be given by desuperheating of the distillate vapor, which is basically this quantity multiplied by, it's basically m dot Cp of the vapor, and the vapor will cool down from TS to T distillate, and then the rest of it will basically be sort of condensation, which is m dot distillate into HFG. So the two equations, this equation is in the cold side of the flow. This is the feed coming in. It will be sensibly heated from TF to TB, and then part of it will evaporate. Here, we are talking about the steam which is entering inside the tubes, that it will be first desuperheated, and then it will condense. The energy which is given by this stream is received by that stream. So when we're looking at that expression here, you can say that what do we have? Basically, we have m dot feed. This is available. We know it. We have obtained it from here. The CP is given to us. TB, TF, MD, and HFG are given. So we have all the parameters which are needed to calculate m dot feed. Do we? When I get back to the equation, we'll find that the value of T feed was not given to us, which means that we are going to make use of that expression first. M dot distillate, we know it. T feed is not known, but M dot distillate is given to us. CP vapor is given to us. We know TS, we know TD, and m dot d and HFG. So we have all the parameters here in the second line, and accordingly, we can calculate the power, 2360 kilowatt. When we substitute this one here, we can get the value of TF that is going to be calculated as 59.46 degrees Celsius. So this is an energy balance for the evaporator, so that we know in the evaporator here we have steam which is leaving the compressor is going to be sensibly cooled first, and then it will condense. So this is the kind of energy given by that stream here, m dot distillate at TS, and it is going to be leaving as m dot distillate at temperature TD. It will enter here as superheated vapor, and it will leave here as saturated liquid. So what we have here basically is superheated vapor, and here this is saturated liquid. To move from superheated vapor to saturated liquid, then there is a desuperheat first, which is from TS to TD, sensible cooling, and then a change of phase. This part, which is given by this line, is what I have been considering here in this equation. Sensible cooling and then condensation. On the other hand, we have feed, which is coming here, that is going first to be heated sensibly from T feed to TB, and then after that it is going to, part of it will evaporate and the rest is going to be heated up and rejected at a temperature TB. And the part that we have in the lower equation here is the part that has been considered by, or the lower curve, the lower line is the one that has been considered by that expression here. And in that expression, we have basically T feed is not given, and we get it from this kind of balance. First, we calculate how much is the heat transfer rate in the evaporator, and the rest is to make use of it to calculate the feed temperature. تفضل يا خالد.
تفضل يا دكتور. One question regarding that. So regarding the compressor here, inlet and outlet, that temperature, the outlet of the compressor is at TS, right?
Yes, exactly. This is the condition which leaves the compressor.
Cool.
And
how
the
about
condition at the inlet of the compressor is this. We have m dot distillate at a temperature T vapor. T vapor is the T distillate, which is less than the brine temperature by the boiling point elevation. So
okay, so
it will enter into the compressor and then it leaves here. Go ahead.
Yeah, T vapor is T distillate minus the brine, right?
TB minus
T
boiling point elevation. The brine temperature minus boiling point.
Yes. Same as the previous for the
Exactly,
Weber
as we did earlier. There's nothing new here.
Cool. Thank you.
Sir,
اتفضل.
is tea vapor same as tea distillate?
It is, yes, it is the same as tea distillate. As a matter of fact, the tea distillate should be a little bit less than the tea vapor by, if you need to be very accurate, because here you have a mist eliminator. So it's, there is some sort of a variation. There's a variation here due to the friction losses in the pipeline. And there is some sort of a small change here due to the pressure loss across the demister. But anyway, we are going to consider them both to be the same because that loss is very minor. So we're assuming both temperatures are the same.
All right, thank you.
You're welcome. Any further questions? If not, then we can continue in the solution, and I'll just clear the board so that we can rewrite again. Right. So what we did so far is that we know what's the value of Q evaporator. We have calculated it. We know the value of the feed temperature. We have also calculated this value. Our next step here is Q for the heaters. Change this to the pen. For the heat exchangers, it is m dot feed. We know the m dot feed, we calculated this 2.5 kilogram per second. Cp feed, which is given to us, and then T feed minus T cooling water. Now, this is going to provide us with the Q for both of the heat exchangers together. And this value can be calculated easily because we know the m dot feed, we know Cp feed, and we know the temperature difference for each one of them. This expression is basically equal to m dot distillate Cp T distillate minus T naught and m dot brine Cp T brine minus T naught. In this equation, what's the unknown? What we don't know here. We know m dot distillate, it's 1 kilogram per second. Cp is given. We know T distillate, it is given. And T naught, unknown. M dot brine, we have it. We have the Cp, we have the T brine, and this one is unknown. So from here, we have only one unknown, which is the value of T naught. So we have written this balance for the two heat exchangers together so that we can calculate the value of T naught. And the T naught here in our example is equal to 26.23 degrees centigrade. Why do we need the T naught? We needed to calculate the areas, if you remember, because we are going to need to calculate the log mean temperature difference for each one of the components. And this is how we can calculate that. One more thing that that we'll need now, we are thinking of areas now. How many areas do we need to calculate? What do you think? How many areas? How many components we have here?
2 areas, 3 areas.
3 areas, that's right. One for the evaporator, one for the brine heat exchanger, and one for the distillate heat exchanger. So if we're going to start with the evaporator, we have already calculated QE, so we know this value. This is in balance with UE, overall heat transfer coefficient in the evaporator. It is given to us. AE, this is what we need, into the temperature difference which is basically TD minus TB. We have this, we have this, we have this, and we have that. So from here, we can simply calculate the area of the evaporator. You see now it is being made easy because we have neglected the sensible heating part. So it's only considering that there's a constant temperature difference and approximately this value can be calculated and the value is 491.6 meters square. Oh, there's a big temperature difference here. There's a big surface area here. If you compare this to the previous examples of the single effect evaporation and single effect evaporation with vapor compression, the values of the areas there were much less than this. Yes, Saleh.
Doctor, in single effect evaporator, we use a TS. Here, why we use a TD?
Yes, because TS in our case here is just a temporary value, which is this. This is TS, and it cools down to 2D. So for the change of phase, the constant temperatures are basically TD and TB. TS has only a sensible part, which if you want to calculate that, then you need to calculate the area based on the log mean temperature difference. But the constant high temperature here is TD. Did you get my point?
Yes.
Fine. Then, if we are going to look at the other two heat exchangers, then the distillate heat exchanger, for example, we have T distillate is going to cool down to T naught in order to preheat part of the feed from T cooling water to T feed. So we can calculate the log mean temperature difference for the distillate preheater. I will not write the expressions because this is basically this difference is delta T1, this is delta T2, so delta T1 minus delta T2 over the natural logarithm of the ratio. This will give us this value as 1.875 degrees centigrade. We have the other heat exchanger in which the brine is cooled down to T naught and the feed is heated up to TF and the log mean temperature difference for the brine preheater is going to be calculated as 0.878 degrees Celsius. Areas then, area of the distillate preheater is obtained from the energy balance. Let me put it in the form of a balance better. That m dot distillate into Cp into T distillate minus T naught. This is in balance with the overall heat transfer coefficient for the distillate, area of the distillate heat exchanger into the log mean temperature difference of the distillate heat exchanger, which is this unit. From here, we can calculate AD, and AD is going to be 44.4 meters square. And then for the other heat exchanger, m dot brine Cp T brine minus T naught. This is going to be U for the brine preheater, area of the brine preheater, log mean temperature difference for the brine preheater, and then from this we can calculate area of the brine preheater, and the area here is going to be 161 meters square. There's somebody who has just joined us now. We'll see that in the report anyway. So Saleh, your question? You have a question, or your hands has been raised from the previous question that you asked?
No, I have a question. Doctor, why, can you repeat why we have a large area of evaporator?
Yes, the large area of the evaporator here, because the temperature difference between TD and TB is quite small. We have a certain Q here, and this Q needs to be transferred. If you are going to transfer it over a high temperature difference, then the surface area will be small. If the temperature difference is small, then this is going to be high. And in our problem, the difference between TD and TB is small. This is why the surface area is too big. Okay. Khalid?
Yes, Doctor, we cannot assume for simplicity that the area of the heat exchanger for the both heat exchanger to be equal, because of the fact that the brine, always the amount of brine is going to be larger than the distillate.
That's right. The amount of the brine will be larger than the distillate, and the temperature of the brine is also different from the distillate. So that you will not have the same the same area, and definitely the seawater which is coming in is not distributed equally. So actually, I was going to tell you now, there's something that I want you to do as an exercise is calculate what's the value of alpha. How much of the fraction of the feed water will go to this heat exchanger and how much will go to that heat exchanger. How can you do that? Who can tell me? I can write here a third equation for the balance that takes care of heating the seawater. For the distillate, it will be
alpha
m dot feed Cp T feed minus T cooling water, isn't it?
Yes.
And one will be, this is alpha, and this is going to be 1 minus alpha into the same thing, m dot feed Cp Tf minus T cooling water. Then calculate the value of alpha, you'll find it's not 0.5, it's not half. So not half of the seawater is going to get to this heat exchanger and the rest will go to that heat exchanger, but it will be different. The high flow rate of the brine will make the temperature difference here smaller. You've seen that in the log mean temperature difference. Here we're having a log mean temperature difference of 1.8, and here we have a log mean temperature difference of 0.8. So the area here is going to be higher. This is 161, whereas this is only 45. So the two heat exchangers are not exactly the same, and this is because of this kind of differences in flow rates and temperatures that we see. What we are left with at the moment is looking at how much is going to be the power consumption. So to do that, I'm going to again erase the upper part of the slide here, so that we can calculate the expression for the power calculations. And basically, we have a compressor with an input stream and an output stream. Actually, just to respect what you have taken before in your thermodynamic course, I'll just put the symbol of the compressor as you have considered it before. It used to be something like this. So the inlet condition to the compressor is here, which is basically P inlet, V inlet, and here we have P outlet or PS and TS. And this is T inlet. Now, P outlet or PS is basically saturation pressure at TS. We know the value of TS, it is given to us. So go to the thermodynamic tables or go to the EES or any property calculator to get the corresponding pressure. And the same thing for this is for the outlet of the compressor. For the inlet of the compressor, the PI or P inlet is basically the saturation temperature at TV or at TD, both are the same. And the same thing, we also need the specific volume, which is the specific volume of saturated vapor at TV. Now we can substitute in our equation here that specific work on the compressor is basically gamma, which is Cp over Cv of the vapor. That's again something that you can get from the properties, divided by efficiency of the compressor. It is given to us, gamma minus 1 into Pi Vi, and the pressure or compression ratio in the compressor, that Ps over Pi to the power gamma minus 1 over gamma minus 1. Now we calculate this and you'll find the value is basically 60.7 kilojoule per kilogram. In order to convert this to the way or the kind of famous expression that which is internationally common to assess the performance, what we can do is that we can take this expression or this value of the work to calculate the power consumption. We can put it that way. Can be given as this value, which is 60.7. We're going to multiply this by 1000 and divide it by 3600 so that it can be expressed in terms of kilowatt hour per cubic meter. The 1000 is the density, so that we convert from mass base to volume base. And the 3600 is to convert from per second to per hour. So that that's the expression that you can use, and then you can estimate the value as how much is the power as kilowatt hour per cubic meter, which is the standard in comparing this kind or in evaluating this kind of units performance. So this is basically the details of calculating the performance parameters as well as the design parameters in terms of surface area for a single effect mechanical vapor compression. The next homework is going to be assigned today, which will be basically talking about the three sub-elements that we have considered in this part: the single effect mechanical, single effect evaporation, single effect evaporation with thermal vapor compression, TVC, and single effect evaporation with mechanical vapor compression. We are not going to leave this part because our next issue to consider is going basically to be how we can make use of the energy which is leaving the unit, which is, for example, if I'm talking about a single effect evaporator like this, and let's assume that it is receiving energy from steam from a power plant or from a compressor like the one that we have considered here. This vapor leaves here as saturated vapor, and this is returned back again to the, or saturated liquid, returned back again to the power plant. So this is from power plant, and this is to power plant. So that the mass flow rate in the power plant is not affected, but we are receiving saturated vapor we take the latent heat of condensation and we send it as saturated liquid. We send it back as saturated liquid. The kind of energy which is given to us here is used for preheating the feed, and part of it will evaporate and the rest is going to be rejected. The streams that are leaving here are basically, we have vapor stream, which is the formed vapor, and we have brine leaving here. The point here is, we said that one of the drawbacks of this system is that we are losing the energy because this vapor is going to be condensed into liquid. So the latent heat of condensation goes by preheating the seawater. This is somehow useful, but this one is thrown away to the environment, and this is a loss. So instead of doing that, we use or we add another unit, another evaporator. This vapor is going to condense, let it condense inside the tubes here. So this is going to be our product, part of the product that we have here. M dot from first evaporator. And the brine which is leaving here is going to be taken. It's still hot. So we can take this quantity and we spray it here. So are making use again. Now this unit or this evaporator number 2 is at a pressure less than the evaporator number 1. So that brine that comes here, it will be saturated. Now there is some losses here in the pressure in the line, and accordingly the pressure reduces a little bit when you bring it here. But when it comes here, because this whole unit is kept at a lower pressure, so it will be saturated. Once it is sprayed over the surface of this hot, relatively hot vapor, it will form another quantity of vapor, which is going to be condensed inside another unit. And the brine which is leaving here is going to be taken to be sprayed here. What are we doing? We are making a series of evaporators so that whatever streams that are leaving here with any potential quantity of energy is made use of here. A formed vapor that will come, that's going to condense here, it will give off heat. Let's make use of the heat to preheat and evaporate some vapor, and so on. And this brings us from a single effect evaporation system into a multi-effect evaporation, and the common name is multi-effect desalination system. So MED, in terms of performance of thermal desalination systems, this one is the best. This one has the highest PR or the highest GOR among all desalination systems. And this is basically what we are going to consider. We have some units of the MED here in the kingdom. In Jubail, Marafiq, we have a multi-effect desalination unit, and this unit is producing more than 800,000 of cubic meters per day. It has like 27 units of these MED systems. Each one of them is having, now we see 1, 2, 3. Typically, we see units of having 8 effects that are there. So the ones in Jubail are 27 units. Each unit is made up of 8 effects, and they are producing 805,000 cubic meters per day. So this is the productivity, and it is quite an efficient unit. It is very much efficient if you compare it with the classic MSF unit, which exists here in many places in the kingdom. So we're going to talk about the basic ideas of the MED and we'll be talking about number 1, the MED, number 2, the MED with thermal vapor compression, number 3, the MED with mechanical vapor compression. So what we did with the single effect evaporation is going to be repeated with the multiple effect evaporation starting from our next class on Wednesday, inshallah. So that would be it for today. And if you have questions, then before you leave, you can leave if you want. I'll be again hanging up for a few minutes so that if you have questions that I can answer. Thank you, ya shabab.
Thank you, Doctor.
دكتور
تفضل.
في الكمبريشن اللي اخذناه الكمبريشن فيبر البراين احنا نستخدمه في اللي هو الهيت اكسشينجر الثاني.
نعم، احنا في العاده البراين كنا قبل كده بنرميه، بس في حاله الميكانيكال فيبر كومبريشن سيستم we can make use of the brine for preheating the feed. اللي هو كنا بنتكلم عنه اليوم.
يكون الميكانيكال افضل بيرفورمانس.
هو مش افضل، لان هو ما زال عندنا مشكله في الميكانيكال ان الميكانيكال باور needed for this unit is substantial كبيره، وبالتالي الانرجي requirements are higher. accordingly لما بتتكلم على الماركت شير بتاعها is not too much. اليونت مبدئيا ما بتكونش كبيره. so far اليونت بتاع الميكانيكال فيبر كومبريشن are limited somehow to something like 5,000 cubic meter per day. بص احنا لسه بنتكلم على اليونت اللي في جوبيل قد ايه. لو بتتكلم على الميكانيكال فيبر كومبريشن محتاج كام يونت هنا؟ محتاج hundreds، كميه كبيره جدا. انما الثيرمال فيبر كومبريشن اللي هو باستخدام الستيم as an input still is more efficient compared to the mechanical unit. لحد ما نلاقي better performance of evaporators، وبالتالي ممكن يحسن الفرصه شويه. لو تفتكر في الاكزامبل اللي احنا حليناه من شويه كنا بنتكلم على الافشنسي بتاعت الكمبريسور في حدود 58 59% which is relatively low. فاحنا what we are looking for is some sort of efficient or energy efficient compression. لو التكنولوجي دي موجوده it will improve the possibilities or improve the opportunities for mechanical vapor compressions to spread. Still it is useful ان انت لو بتتكلم على remote area انت محتاج كميه ما هياش كبيره من السويت ووتر عشان مثلا كوميونتي صغيره او عشان قريه ولا شيء، وفي عندك ديزل انجن so that's something that can provide you with a good way a compact unit to produce sweet water. انما كenergy efficiency it is still the energy consumption is on the high side for these units. Did I answer your question, ya Saleh?
Yes. Thank you, Doctor.
Further questions يا شباب؟ ما كانش that would be it for today. Dawood, you have any questions or comments?
No, but I just wait to listen the questions of my friend.
Okay, طيب. Abbas?
لا دكتور.
طيب اوكي. طيب يا شباب اشوفكم يوم الاربعاء ان شاء الله باذن الله.